For these problems, what we're going to do is we're given some rectangular coordinate graphs that hopefully are pretty easy to recognize. And then what we're going to do is we're going to convert them into polar equivalents. Some things make a lot more sense in polar. They're actually really nice and convenient. Others are not. So what we want to do is kind of develop some familiarity about going back and forth, because in sort of a real world scenario, a lot of times what you're going to do is you're just going to pick the one that's convenient. So it's helpful to be able to go back and forth and go, oh, that's terrible, that one's better. So the first one is x squared plus y squared equals 16. Now, you know the graph of this thing, right? That's x squared plus y squared equals r squared, right? That's the whole point, is that's the equation of a circle, and the circle of radius 4. So, right, I've got a circle of radius 4. Not the prettiest circle, but that's okay. The next one is y equals 5. Now, y equals 5 is just a flat line. So there's no reason to have to overthink this. This is y equals 5 here. That goes through y equals 5, and then just it's a horizontal line all the way across. And finally, y squared equals 6x. Now this is a parabola, but it's not the standard y equals x squared parabola that we're used to. It sort of looks like a square root, or it looks like a parabola got kicked over, right? So we did a section on conics recently, so hopefully you know enough about that you could draw that, right? You draw your directrix and focus, and you could really pretty it up if you want to. No problem. Feel free to do that. But in this case, what we're trying to do is we're trying to figure out how to convert this into a polar equation. So what we want to do is we want to use these things here. We want to put all those together to develop some nice things. Now, typically when you have rectangular to polar, you leverage these. Now you don't have, these aren't, this is the typical way, but don't forget about this one. This one's a big one. If you can, this is a lot better, this is a lot more useful whenever you can. Because I could plug these in here and simplify, or I could say, this is right here. So r squared, x squared plus y squared is r squared. So now r equals 4. Now this is really nice. This is really, really, really nice, because this is a super compact notation. It says, instead of having x and having two variables, you have one. And it just says r equals 4. Oh, that's just the case where the distance is always 4. Well, that's the circle of radius 4, because no matter what, the radius, or the distance, is always 4. Now, it's not on this horrible thing that I drew, but it is if it's an actual circle. So this is actually a much more convenient notation in polar, based, if you ask my opinion. Now, the next one, y equals 5. This one I think is not more convenient as a polar equation. So y is r sine theta. So we have r sine theta equals 5. And typically when you have something in a polar equation, this is technically correct. This is probably fine. But what they typically want is r as a function of theta, so you have all the r's on one side and all the thetas on the other, if you can help it. And that's not always possible, but if you can help it. So this is technically r equals 5 cosecant theta. Now, this I don't think is a very useful representation. I think y equals 5 is very clean, very compact. This is kind of disgusting. I wouldn't, if I looked at this, and I would have to convert back to rectangular to have a better, to be like, what in the world am I looking at? So I don't like that in general. And finally, you have this. Now, this isn't super pretty. A lot of people aren't used to y squared equals an x. So that can require kind of wrapping your head around it. But let's plug some things in here. So I'm going to get that r sine theta squared equals 6r cosine theta. Again, I'm just replacing x and y with those, which gets me r squared sine squared theta 6r cosine theta. So then what we would want to do is we would want to divide both sides by the r. We would get r sine squared theta equals 6 cosine theta. And then we would move everything that's not r to one side. So we would say r equals 6 cosecant squared theta cosine theta. Now, that's one way to write that, and that's perfectly fine, perfectly acceptable. A way I would probably prefer to write this is r equals cosecant theta cotangent theta. There's a couple of reasons for that. One is that if I were to, like, for some reason be doing something like an integral of that, then this comes out a lot more cleanly. Cosecant cotangent is more used in identities than cosecant squared times cosine. So it really just depends on what your usage is, but that's, you ask me, that this is the better representation. Either way, I don't like those. I don't think they're very great representations. I'd much rather have this. I think a lot of us would rather have rectangular, but it can be very convenient in some cases to have that. There are other representations that, like the case of r equals theta, like you don't want to do that in rectangular. You really can't do that in rectangular, not in an easy way. So this is there's certain things that just kind of have to be in polar. So get comfortable with it. Do some examples. Get yourself able to do these types of problems.